Hello, my name is Hunter Chase. This is joint work with James Freitag. Our work occurs in the setting of equivalence and membership query learning. So for the setup of this, we let C and H be two set systems, or I'll sometimes refer to them as concept classes, on a base set X, all of which may be finite or infinite. So in the query learning setting, the learner is attempting to identify a target set A in the class C using membership queries, where we can ask about a particular element and find out whether or not it's in the target, or equivalence queries from H. So we can submit any set from H as a guess. If we manage to submit the target set, then we've succeeded. Otherwise, we will get a counterexample, some element that is in our hypothesis, but not in the target, or vice versa. Um, and so our goal for this will be to bound the worst case number of queries I needed to learn any A and C. So if we have, we'll say that a class is learnable if and only if there's some n such that any set in C can be identified in at most n queries of either type. And we will let LC EQ plus MQ denote this best upper bound. So we're looking to identify some quantities that allow us to bound this bound the worst case number of queries. And the first quantity that we'll look at is Littlestone dimension. So the setup for Littlestone dimension is we have this binary element tree. This is a binary element tree of height 3. The intermediate nodes are all labeled with elements from the base set X, and the leaves are labeled with sets from C. And a leaf is properly labeled by a set when all of that set's predecessors, their membership in C is determined by the path that we take to get to C. If we're below and to the right of an element, then everything below and to the right should contain that element. Everything below and to the left should not. So anything below and to the right of a empty set should contain empty set. Anything below and to the left should omit a empty set. So here C101 will be properly labeled if it contains a empty set and A10, but omits A1 with no condition on any of the other elements appearing in the nodes. So the Littlestone dimension of a class is the maximum depth of a tree where every leaf can be properly labeled from C. And it's not too difficult to see that C must have finite Littlestone dimension in order to be learnable by queries. Essentially, we need to be able to reduce the Littlestone dimension of the class of all remaining possible concepts to 0. If we've reduced the Littlestone dimension of that class to 0, that means that there's only one possible set remaining, which must be the target, which we then can submit and succeed. If the Littlestone dimension is infinite, then we're not going to be able to reduce Littlestone dimension to 0. No matter what kind of query we submit, there's always the possibility that we'll get back a query that keeps the Littlestone dimension of the remaining possible concepts infinite. So this is the first quantity that we consider. It was originally identified by Littlestone. but hasn't been used much in query learning since then. The other quantity that we look at is consistency dimension, which has been used in query learning before. So here, first I have to talk about what it means to be n-consistent. Take some subset of X, and we'll identify this subset with its characteristic function. And we'll say that it's n-consistent with C, with the class C, if for any trace of this function on n elements, there is some set in C which behaves the same way on some n elements. So if we're looking for 5 consistent, for every 5 tuple, for every set of 5 elements, we need to be able to find some set in C that behaves on those 5 elements the same way that A does. And the consistency dimension of H with respect to C is going to be the least such n such that whenever we have a set that is n consistent with C, then we can find that set in H. If no such n exists, then we say that the consistency dimension is infinite. The consistency dimension must be finite in order for the class to be learnable with queries from H. Why is this? Suppose, so if we have an n-consistent, if we have a set A that's n-consistent with C, but it's not in H, then no matter what queries we submit, an adversarial teacher can always return information that sort of points towards A for at least n many steps. So if we submit a membership query, then the teacher could respond with whether or not that element is in A. And if we submit an equivalence query, we can find a counterexample with respect comparing the query that we've made with A. And because A is not in H, we know that A hasn't been submitted as a query. So an adversarial teacher can force us to, or can simulate A for at least n many queries, and so it'll take at least that many queries to identify a target. And so if there's no bound on this n, which is to say if the consistency dimension is infinite, then we're not going to be able to establish a uniform bound on the number of queries we need to learn. So I've sort of argued why each of these quantities has to be finite in order for learning to be possible. But these quantities being finite also characterizes when learning is possible. In particular, if both of these quantities are finite, then we can establish an upper bound on the worst case number of queries that is essentially Littlestone dimension times consistency dimension. And if either of these quantities are infinite, then we don't have learnability. And the proof of this gives an algorithm where the strategy is to systematically reduce the Littlestone dimension of the class of remaining possible concepts to 0. Once we've reduced it to 0, there's only one remaining concept remaining. We submit it, and we've won. Our contributions here, so there are at least two aspects in which this is a new contribution. The first is that these bounds work whether or not C is finite or infinite. Previous bounds were only known when C is finite, and they only used log of the size of C rather than the Littlestone dimension of C. So our other contribution is to use the Littlestone dimension of C as a more appropriate measure of the complexity, which allows us to study infinite classes as well. We can also use these bounds to study efficient learnability. So in this case, we're studying a family of classes indexed by n, and we can ask that the worst case number of queries is bounded by a polynomial in n. Now, if we look at the bound that we got on the previous slide, we get essentially Littlestone dimension times consistency dimension. So we get a bound which is polynomial in Littlestone dimension and consistency dimension. We can also find lower bounds which are linear in Littlestone dimension and linear consistency dimension. So in particular, as long as both Littlestone dimension and consistency dimension are themselves polynomially bounded, we will get efficient learnability of this family of classes. And that gives a characterization of efficient learnability. We can use this to reprove previous results of efficient learnability of well-known cases. Most notably, we give a new proof of efficient learnability of regular languages or deterministic finite automata on n states. And so the strategy for this is to calculate the consistency dimension, which can be done using the Myhill-Nerode theorem, and also to calculate the Littlestone dimension of this class, which in this case, it's enough to just look at the cardinality of this class. So we show that those are both polynomially bounded in n, and that gives us efficient learnability of this class. One other novel aspect of this is the proof or the bound that we give does not rely in any way on the length of the words that we receive as counterexamples or submit as queries. The bounds are only in n. A couple of remarks about other problems in this area. I've talked about learning with both equivalence queries and membership queries. We can also look at what happens if we only have access to equivalence queries. We are able to give a characterization of learnability, but not efficient learnability, as the upper bound that we get is exponential. And in this case, consistency dimension doesn't seem to be the right parameter. There are potential alternatives, namely the strong consistency dimension, but we don't have efficiency results. We've also looked at the worst case scenario, or the worst case number of queries, which is essentially assuming an adversarial teacher, a teacher giving us the least informative information that they can. We can also look at what happens if counterexamples are randomly selected, and look to bound the expected number of queries. When C is finite, we can give a bound that is 2 times the Littlestone dimension. And I should say that this is not in this paper. This is other ongoing work. And we're also looking at possible ways of extending this to infinite classes. So that's all I have. Many thanks for your attention.